Welcome friends to another session on mathematical modeling. We will discuss urban wastewater management planning in this session. Urban wastewater management planning. By way of a hypothetical example, we shall describe how decisions are made to expend public monies to control water pollution in a river system. Federal guidelines require that the technical, economic, financial, environmental and socio-political aspects of the problem is evaluated. Thus, multiple and often conflicting objectives exist. Also, planning is undertaken on an area-wide or river basin level, wherein we must deal with numerous political jurisdictions. The analyst, especially if he is trained only in one discipline, has a strong tendency to define the problem as being one that requires primary input from his areas of specialization. The hard question is to try to allocate successfully the available resources in such a way that the highest assurance of making the correct decision is obtained. The quality of the analyst's effort is gauged by the quality of the information for making the decisions and not on their independent value as worthwhile scientific investigations. The example will describe a hypothetical case. After reading through the case, you can explore numerous avenues of inquiry within this general framework. The main character in the scenario is a practicing professional who is trained in mathematics and has had some exposure to the social sciences and engineering. Description of the study area and the scenario. The urbanized area is comprised of three cities, Thralsville, Bramsberg and Straffin, which are presently discharging raw sewage to the nearby Lucas River. The general location map is shown in figure 1. Each city is required to reduce the pollution by constructing sewage treatment plant alone or in conjunction with other cities. You are the head of the Perry County Planning Department. In addition to a small technical staff, you are able to consult with faculty from nearby Berkshire University regarding spatial problems. After some preliminary discussions with your staff, you decide to examine the technical aspects of the problem first. Environmental engineering design. Professor Foster advises you that the pollution control regulations require that a secondary treatment plant be installed at each of the cities. Such a plant removes 90% of the pollution. You are hoped to remove all of the pollution, but he says that it is technically infeasible. The cost of a secondary sewage treatment plant can be estimated using CT is equal to 73 lakh into Q raised to 0.712, where CT is the present value of the capital plus operation and maintenance cost based on 8% interest over 20 years, and Q is the wastewater flow in cubic feet per second. Note that there are economies of scale in building sewage treatment plants, that is, delta C by delta Q decreases as Q gets larger. Thus, it may be cheaper to pipe the wastewater from Thralsville and Bramsberg to Straffin and construct a single larger plant. Piping cost can be estimated using Cp is equal to 6600 into Q raised to 0.51 into L, where Cp is the present value of capital plus operation and maintenance cost based on 8% interest over 20 years. Q is the wastewater flow in cubic feet per second and L is the pipe length in 1000 feet. Economic analysis. Professor Gibbs, a resource economist, describes pollution as an external diseconomy, that is, the production decisions of one unit in the system impose adverse effects on other units. He explains a model of a rational economic man seeking to maximize profits or minimize costs given certain technological alternatives, associated price and cost guides. Within the context of your problem, he asks you to find the least costly way of meeting the specified pollution control standards. With only 3 cities, he suggests that you enumerate all possibilities. The results are shown below. Option 1, each city build its own plan, that is C of 1 is equal to 7,30,000 into 5 raised to 0.712, which is equal to 23 lakh. C2 is equal to 7,30,000 into 3 raised to 0.712, which is equal to 16 lakh. C of 1 is equal to 7,30,000 into 5 raised to 0.712, which is equal to 23 lakh. So, the total cost is 62 lakh. Option 2, cities 1 and 2 consider a plant at 2, city 3 builds its own plant, that is C12 is equal to 7,30,000 into 5 plus 3 raised to 0.712 plus 6,600 into 5 raised to 0.51 into 20, which is equal to 35 lakh, and C1 plus C2, which is equal to 39 lakh. C of 1 2 is equal to 35 lakh and C of 3 is equal to 23 lakh. Therefore, total cost is equal to 58 lakhs. Option 3, city 1 builds its own plant, cities 2 and 3 consider a plant at 3, that is C of 2 3 is equal to 7,30,000 into 3 plus 5 raised to 0.712 plus 6,600 into 5 raised to 0.51 into 38, which is equal to 36 lakhs 50,000. C of 2 plus C of 3 is equal to 39 lakh, that is C1 is equal to 23 lakh and C23 is equal to 36 lakh 50,000. Therefore, total cost is equal to 59 lakh 50,000. Option 4, city 2 builds its own plant, cities 1 and 3 consider a plant at 3, that is C of 1 3 is equal to 7,30,000 into 5 plus 5 raised to 0.712 plus 6,600 into 5 raised to 0.51 into 58, which is equal to 46 lakh 30,000, and C of 1 plus C of 3 is equal to 46 lakh, that is C13 is equal to 46 lakh and C2 is equal to 16 lakh. Therefore, the total cost is equal to 62 lakh. No better option 1, delete from further consideration. Option 5, cities 1, 2 and 3 consider a plant at 3, that is C123 is equal to 7,30,000 into 5 plus 3 plus 5 raised to 0.712 into 20 plus 6,600 into 8 raised to 0.51 into 38, which is equal to 55 lakh 60,000. C12 plus C3, which is equal to 58 lakh, C23 plus C1, which is equal to 59 lakh 50,000, C13 plus C2, which is equal to 62 lakh. Therefore, C123 is equal to 55 lakh 60,000. Thus, from the viewpoint of economic efficiency, the best overall solution is to pipe the wastes from Thralsville and Bramsberg to Straffin and build one large plant at that point. Financial analysis. Given that the costly solution is a single plant, some mechanism is needed to apportion this cost among the 3 cities. Experts on public finance say that there are numerous ways to assign these costs. The method most commonly used in waste treatment field is the use of facilities method. The procedure is to assign each city a share of the cost based on its proportional share of the use measured in flow rate. We decided to follow this seemingly reasonable procedure. The results are presented in the following section. First one is Thralsville. Pipeline from Thralsville to Bramsberg is 3 lakh. 5 by 8 of pipeline from Bramsberg to Straffin is 4 lakh 50,000. 5 by 13 of treatment plant at Straffin is 17 lakh 45,000. Therefore, the total cost is 24 lakh 95,000. Next is Bramsberg. 3 by 8 of pipeline from Bramsberg to Straffin is 2 lakh 74,000. 3 by 13 of treatment plant at Straffin is 10 lakh 46,000 and the total cost is 13 lakh 20,000. Third one is Straffin. 5 by 13 of treatment plant at Straffin is 17 lakh 45,000 and the total cost is 55 lakh 60,000. This cost sharing procedure does apportion the entire cost of the project among the 3 cities. We should like to check how each city would react to this arrangement. The results are disappointing, for while the overall plan is financially better for Bramsberg and Straffin, it is more expensive for Thralsville, that is 24 lakh 95,000 versus 23 lakh. Experts point out that this situation sometimes occurs. They suggest that you might find some concepts from cooperative n% game theory to be helpful. The use of game theory is very helpful. Its axioms of fairness, would not allow Thralsville to be assessed a cost that is higher than its cost of independent action. It is straightforward to construct a 3% cooperative game in characteristic function, wherein the characteristic function is defined as the savings to a coalition from cooperation. Thus, the savings into 10 raised to 3 are V of 1 is equal to V of 2 is equal to V of 3 is equal to 0. V of 1 2 is equal to C of 1 plus C of 2 minus C of 1 2, which is equal to 400. V of 2 3 is equal to C of 2 plus C of 3 minus C of 2 3, which is equal to 250. V of 1 3 is equal to C of 1 plus C of 3 minus C of 1 3, which is equal to 0. V of 1 2 3 is equal to C of 1 plus C of 2 plus C of 3 minus C of 1 2 3, which is equal to 640. Note that coalition given in equation 13 is essential, that is V of 1 3 is equal to V of 1 plus V of 3. The set of imputations and the core of the game are shown graphically in figure 2. The equilateral triangle ABC delimits the set of imputations, that is x of I is greater than or equal to 0 for I equal to 1 2 3. Summation x of I is equal to V of 1 2 3, where xi is the savings allotted to player I. The additional constraints to delimit the boundaries of the core are: first one, x of 1 plus x of 2 is greater than or equal to 400, which is bounded by allotting 640 minus 400 units to x of 3, and the balance is either x of 1 or x of 2. Thus, the two additional data points are 400 0 240 and 0 400 240. Second case, x of 2 plus x of 3 is greater than or equal to 250 generates two additional data points 390 250 0 and 390 0 250. Third case, x of 1 plus x of 3 is greater than or equal to 0 generates two additional data points 0 640 0 and 0 640 0, which are simply the original point B, since the coalition is inessential. The core is shown as the shaded portion of the equilateral triangle. We would like our cost sharing point to fall within the core. In general, at most 6 data delimit the core boundaries. In this example, they are counting the point B twice. First one 400 0 240, second one 0 400 240, third one 390 250 0, fourth one 390 0 250, and fifth one 0 640 0, and the sixth is 0 640 0. Professor Packel suggests that the Shapley value might give a reasonable solution. Shapley assumes that each member should get the incremental value he brings to the coalition averaged over the n factorial coalition formation sequences. In this case, the sequences are 1 2 3, 2 1 3, 3 1 2, 1 3 2, 2 3 1 and 3 2 1. Thus, x of 1 is equal to 1 by 3 into V 1 minus V of 5 plus 1 by 6 into V 1 2 minus V 2 plus 1 by 6 into V 1 3 minus V 3 plus 1 by 3 into V 1 2 3 minus V 2 3, which is equal to 1 by 3 into 0 plus 1 by 6 into 400 plus 1 by 6 into 0 plus 1 by 3 into 640 minus 250. That is, x of 1 is equal to 196, where V of 5 is equal to 0. Similarly, x of 2 is equal to 322, x of 3 is equal to 122. Note that summation x of I is equal to 640. This solution is in the core. Indeed, it is the same solution you would get if you simply averaged the above 6 corner points. Thus, you are satisfied that the financial arrangements are reasonable. Environmental impact statement, ecology. The results of the economic analysis indicate that the option 5 greater than 2 greater than 3 greater than 1 state environmental regulations require that an environmental impact statement be prepared. The ecology professor suggests an intensive field survey of the Lucas River. Following this investigation, the study team recommends that 3 plants be built because of their better reliability. Thus, option 1 is their first choice, followed by 2 or 3, with 5 being their lowest choice. This really complicates matters since the ecologists' and economists' solutions are in direct conflict. Furthermore, attempts to relate reliability to dollars prove futile. Thus, we are at an impasse. Also, in accordance with the environmental regulations, a public hearing to elicit citizens' input is required. This is the next item on the work plan. Public participation. Our next step is at the Department of Speech and Communications to get some insight into how to organize a public hearing. After lengthy discussion, you decide to hold a televised meeting at Bramsburg High School auditorium. As director of the planning staff, you chair the meeting with members of your staff available to answer questions. A brochure describing the alternatives and their economic, environmental and financial implications is sent to every taxpayer in Perry County. The meeting is a lively one with many people making presentations. Highlights as reported in the Bramsburg Bugle are listed. First one, members of the accolade feeling that Plan 1 must be selected irrespective of cost. We cannot afford to risk killing the river. Second one, the Lucas River Canoe Association favors Plan 5 to keep the river unpolluted upstream of that point. Third one, Mayor of Thrallsville strongly favors building his own plant to stimulate the economy of his area. Fourth one, numerous upper income residents from Straffin oppose Plan 5 because they do not want to have sewage from other cities transported to their city. Fifth one, the Perry County Board of Education, while sympathetic to environmental control, feels that it is more vital to initiate the middle school construction program that has been delayed for 3 years due to lack of funds. They present a petition with 1,000 signatures. Sixth one, a retired lawyer questions the legitimacy of the public hearing. He wants to know how the final choice is to be made. Seventh one, the citizens against higher taxes urge support for a Plan 5 because it is the least costly. Eighth one, Mayor from Straffin protests that his city should pay less than recommended by Plan 5 because they have to put up with the numerous inconveniences associated with the construction. Ninth one, Mayor from Bramsburg urges that Straffin should pay a larger share of the cost because they will gain jobs for their constituents. Overall, the hearing lasts 6 hours, during which 500 pages of testimony are submitted by 83 people. We can now realize that it is a sensitive issue. Next, you contact Professor Mayer to see if she can suggest techniques from political science that might prove helpful in resolving this issue. Political science. The knowledge in political science make a frequent mention of one man, one vote as the appropriate principle to select the best plan. Thus, your first thought is to set up a county-wide referendum to choose among the various alternatives. You describe this proposed procedure to your advisors and receive the following reactions. First one, Professor Foster, your engineering advisor, opposes the referendum. He feels that this is a technical question that should be decided by the experts. Politics should be kept out. He recommends that the technical staff should make the decision. Second one, Professor Gibbs, the economics consultant, is opposed to considering any plan other than 5, the economically optimal one. He feels it would be irrational to select any other plan. Third one, Professor Mayer feels that 4 alternatives are too many to consider in a referendum because the voters will be confused. No plan is apt to receive a majority of votes, so that a runoff would be necessary. Fourth one, each mayor feels strongly that the chosen plan should be favored by a majority of his constituents. This would require additional referenda. After consulting with Professor Mayer, you decide to reject suggestions to let the experts make a selection. You are convinced that this is a social choice problem wherein we shall, by some mechanism, aggregate the preferences of all individuals into a single social choice mechanism. Professor Mayer advises that no single best way to determine the appropriate social choice exists. She does suggest evaluating the relative power of the various cities using the Shapley-Shubik index that is identical to the Shapley value, except that the characteristic function is defined as follows. V of S is equal to 1 if S is a winning coalition, 0 if S is a losing coalition. Thus, V of S minus V of S minus I will be 0 if player I joins a coalition that is already a winner or joins a losing coalition that remains a loser with player I. Only when player I converts a losing coalition to a winning one is he pivotal. His relative power depends on the number of times he is pivotal. Allotting 1 vote per 1000 persons requiring a simple majority to win, then a 3 city quota game can be constructed. Let Q W1, W2, W3 denote the quota game, where Q is the quota needed to win and Wi is the number of votes owned by player I, where I equal to 1, 2, 3. For this case, the game is 136, 100, 60, 110 and the coalition formation sequences are listed. The pivot is underlined, that is 1, 2, 3, 2, 1, 3, 3, 1, 2, 1, 3, 2, 2, 3, 1 and 3, 2, 1. For this case, the Shapley-Shubik index expressed as the vector phi is phi is equal to 1 by 3, 1 by 3, 1 by 3. All cities have equal power. This seems unfair to the two larger cities. Next, a 2/3 quota is used, or 181, 100, 60, 110. The resulting vector is phi is equal to half, 0, half. In this case, Bramsberg is powerless, or in game theory parlance it is a dummy. Thus, this approach is rejected. In general, city 2 has relative power of 0, 1 by 6 or 1 by 3 depending on the quota. His nominal relative power is 60 by 270, which is equal to 0.22. Thus, he is either under or over represented. Similar results occur for Thralsville and Straffin. Thus, this procedure is abandoned. Representatives from the 3 cities meet with the technical staff to try to reduce the number of alternatives under consideration. After lengthy discussion, it is decided that alternative 3 can be eliminated because it is dominated by alternative 2, since its cost is higher and it offers the same environmental quality. For the remaining 3 alternatives, each city is asked to rank the 3 alternatives denoting by A for their first choice, B their second choice. The result are given. First case, 3 plans, city 1, 2, 3 is given as A, C, B. Second case, 2 plans, B, B, A, and third case, 1 plan, C, A, C. Clearly, no plan is unanimously preferred. Plan B does offer 2 cities their second choice and 1 city is first choice, so it would be expected to be preferred. But city 1 opposes this solution because it does not feel that city 2 should receive equal representation due to its smaller size. Before concluding, let us summarize what we have learned in this session. This session is designed to provide a scenario for the mathematical modeling course that seeks to examine applications of mathematical principles to an important public decision making problem. Following presentation of the technical, economic, environmental, social and political aspects of the problem, the students can pursue several avenues of inquiry ranging from repeating the same type of analysis with a modified set of assumed conditions to in-depth evaluation of one phase of the study. The session is oriented toward illustrating the role of models in a particular decision making process rather than emphasizing modeling as the end product. Here are few problems you can try out for the better understanding of the topic. First one, in the problem studied in the session, after the discussions which we have made, what would you do? Justify your answer. Second one, you describe about the problem of urban water pollution in your city and come out with a wastewater management plan. The following are a list of references for further reading. First one, Discrete Mathematical Models by F.S. Roberts, Prentice Hall Incorporated, 1976. Second one, Modules in Applied Mathematics Volume 2, Political and Related Models by Stephen J. Brams, William F. Lucas, Philip D. Straffin Jr., Springer Verlag 1983. Third one, Brebbia C.A., Mathematical Models for Environmental Problems, John Wiley and Sons, New York 1976. Fourth one, Kenneth T.M. and Vanelista M.P., Mathematical Modeling for Water Pollution Control Processes, Ann Arbor Science Publishers 1975. With this, we come to an end of the sessions on mathematical modeling. Goodbye.